Alrighty, morning everybody. Welcome back to Complex Analysis, and hello to you too, Sarah. Hope you're enjoying life sitting around at the airport right now as you watch this. So yeah, Sarah's going to be out of town for the next couple of days. She okayed it with me ahead of time. Let's safe travels. So, plan for today is we're going to jump headfirst into what I'm going to call the Calc 1 portion of this class by focusing on what does it mean to take a limit of a complex function as well as a complex sequence of numbers. We'll put Calc 2 in there as well, I guess. And then towards the end of class, focus a little bit on continuity so that tomorrow we will be ready to start talking about what it means for a complex function to be differentiable. I've got office hours this afternoon from 1 to 2. And I posted a new homework assignment, homework 4, which will be due on Tuesday next week. Decided to pick it Tuesday instead of Monday just because I'm not going to be able to do office hours tomorrow afternoon. And I want to make sure you all have the opportunity to come in on Monday and talk to me about homework for it's actually due. So don't forget though, you do have a homework set due tomorrow as well as one due today. So make sure I have that before you head out for the day. Any questions or comments before we get started for today? Here's a question for you. Are monsters good at math? In general, the answer is no. Not unless you count Dracula. Okay, so yesterday we kind of talked about a bunch of different topics that were kind of disparate topics, not really super related to each other. Finding nth roots of complex numbers, talking about different types of sets like open and closed sets in the complex plane, as well as introducing the idea of complex functions and what it means to kind of try and sketch a graph of what the complex function does going from one set to another set. And what we're going to be doing today is we're going to be introducing the idea of limits. So we're going to have two different types of limits that we're looking at today. The first type of limit is looking at the limit of a complex sequence. So if you have a sequence of numbers, what does it mean for that sequence to converge? And then in the second part of class, we'll focus on looking at complex functions and say, like, if we wanted to look at f of z equals z squared, how do you take the limit as z approaches I of something like that? And if you've taken real analysis, a lot of the definitions that we're going to be doing today are going to be somewhat familiar, just with different types of pictures attached to them. And if not, we're going to be talking about limits in a more formal way than your typical Calc 1 class. Where, Caleb, for instance, what would your intuition tell you should do if you wanted to take a limit as z goes to I of something like z squared?
Put in I for z, so I squared, so it would be -1.
Yeah. In that case, we would this is something where we could just plug in I for z and get -1 all hunky-dory. Katrina, how would you approach this limit, do you think?
Well, if you try to plug in 1, you get divided by 0, which is bad. So
Yeah, we don't want to do that.
you can't do that.
Even in a class with imaginary numbers, we don't want to divide by 0 if we can help it.
Yeah, so probably I would try to factor the top maybe into z plus 1, z minus 1, and cancel it out. Swoosh, swoosh the z minus 1s, and then you can plug in 1 and get z plus 1 plus 2.
Yeah, so in general, I'm sure you've all seen plenty of examples in past math classes of limits like this, where sometimes you can just plug in your value that z or x or whatever is approaching into the expression to get what your limit is. Sometimes you can just, sometimes you can't do that, but there's a little bit of trickery you can do by saying, well, you can't, this is undefined at z equals 1, but if we kind of cancel out factors of z minus 1 in the top and bottom, then suddenly we get something where we can plug in 1 and 2 and get a limit that makes sense. What we're going to be doing today, though, is we're going to be talking about how do you make the idea of a limit more precise. And saying something like, as z gets close to I, z squared is going to get close to I squared. It's like, it's because in Calc 1, typically when you see these sorts of limits for the first time, it's a little bit hand-wavy, a little bit janky. So what we're going to do is we're going to get some Greek letters involved today, specifically epsilon. And you talked about how you can make the definition of a limit a little bit more precise. So to start with, what we're going to say is a sequence limit, because I think the sequence definition is a little bit easier to work with and get some intuition wrapped around it. Or what we're going to say is that a sequence of complex numbers is going to converge or have a limit, has a limit of, however you want to describe it, a fixed point z naught if for all epsilon greater than 0 there exists a big N in the natural numbers such that if little n is greater than big N, then the distance from z sub n to z naught is less than epsilon. What on earth does any of that mean? Let's draw a picture and see if we can figure that out. So what I want to do, actually, let's get the axes out of the way. So let's draw a picture and see if we can kind of understand what this definition is trying to say. So what this is saying is that we are going to try and look at what happens if we have a sequence of points in the complex plane. So we could have a sequence that's something like I to the n over n, for instance, which will give us the sequence I squared over 2, I cubed over 3, I to the 4th over 4. Basically, an expression that we can plug in different values of n for and get this sort of infinite sequence of complex numbers. And what I want to do is see what happens if we kind of pictorially represent that and see what does it mean for that to converge. So let's say we have a sequence of points in the complex plane that is going to look something a little bit like this. Where we have a z1, a z2, a z3, a z4, a z5, and a z6, with the idea that as we keep going further and further out in our sequence of points, there's this sort of fixed point here at z naught that all of the points in our sequence are tending to get closer and closer to. And so, Ginger, intuitively, why would you say that it looks like this sequence is converging to z naught in the picture?
The bigger n gets, the closer we're getting to z naught.
Yeah, the bigger n gets, in other words, the further out we get in the sequence, we're going to get closer and closer to z naught. So that, pretend I drew infinitely many dots on the board. if we were to look at z sub 500, we're going to be getting a point that's extremely, extremely close to z naught. And if we did z sub 1,000, z sub 2,000, z sub 1,000,000, we'd be getting even closer and closer to that fixed point z naught. And the question I want to ask is how can we prove, or how can we kind of visualize at least this definition of proving the limit converges to z naught using this idea of epsilons. So, Katrine, what does epsilon represent?
It's something greater than 0 and it's like a distance.
Yeah, it refers to a distance. So, epsilon here is this Greek letter, sort of looks like an E. It is not an E, do not be fooled. Cough, cough, Adam Stacy. But the idea here is I'm going to draw some positive distance epsilon in the complex plane. And we're going to draw a little disk centered at z naught of radius epsilon. Let's call this epsilon 1 right here. And here's my question. Given this value epsilon 1 that I've just kind of drawn out in this picture, I claim that past a certain point in our sequence, every term in the sequence is going to be inside of this disk of radius epsilon 1 around z naught. So, Caleb, how far out in the sequence do we have to go before suddenly every single term in our sequence is within distance epsilon 1 from z naught?
A radius out to, or actually a little bit past z1.
Yeah, a little bit past z1 would do it. So, maybe, let me rephrase my question a little bit. Is z1 going to be within distance epsilon 1 from z naught? So looking at this picture, is z1 inside of this sort of disk centered at z naught?
Not now.
I'd say z1 is too far away. How about z2?
No.
How about z3?
That one's good.
z4?
Yep.
z5?
Yep.
z6?
Yep.
z sub 100?
Yep.
z sub a billion?
Yep.
Z sub 7 trillion?
Yeah.
So in other words, it's sounding like what you're telling me, Caleb, is that once we get past the first couple of terms in our sequence, everything past that point in the sequence is within distance epsilon 1 from our fixed point z naught.
Mm-hmm.
Gary, would you agree with that?
I agree.
Cool. So if we look at our definition, what is it saying? It's saying if you give me some epsilon value greater than 0, like let's say this epsilon 1 here, there should come a point big N in this set. Ginger, refresh us. What is this set fancy looking N here?
The natural numbers.
Yes, this is a set of natural numbers.
What are the natural numbers?
Good question. Katrine?
Like positive integers, not 0, 1, 2, 3, etc.
Yeah, basically just positive integers. So like 1, 2, 3, 4, 5, dot, dot, dot. There should exist some natural number, some positive integer, where if we take a little n that's greater than that big N, suddenly the distance from that little nth term in your sequence to z naught has to be less than that epsilon tolerance we established, the distance from z naught that we're allowed to get. So Caleb, you just told me that past the second term in the sequence, every single following term is within distance epsilon 1 from z naught. So what we can say is, given this epsilon 1 that I've drawn out on the board here, I think what we can say is if big N is equal to 2, then whenever little n is greater than that value, little n is greater than 2, the distance from the little nth term in our sequence to z naught is going to be less than epsilon 1. Again, absolute value of z sub n minus z sub naught refers to distance between the 2 points. So in other words, if you pick any term in the sequence, z sub little n, as long as you're past the second term in the sequence, you're looking at z sub little 3, z sub little 4, z sub little 5, etc., etc. According to Caleb, all of those points are going to satisfy that their distance from z naught is less than epsilon 1, meaning they're all in this sort of disks centered at z naught of radius epsilon 1. So what this tells us is for this specific value of epsilon, given this epsilon 1, you can find a point in the sequence past which everything has distance from z naught less than that fixed distance epsilon 1. Sound good? Alright, I just realized I forgot my color chalk. Hold on just a second. I got yellow chalk now. Let's look at the same picture, but I'm going to draw a new epsilon out. Yes?
What does the n equals 2 and the little n equal 2 mean?
So here, 2 is taking the place of this sort of big N, and it's saying big N equals 2 corresponds, how far out do you need to go before every following term is within the distance that you
So not
set?
the term itself, but everything following it. That's
Correct.
why it's greater than, not greater than, equal to.
Yeah, as you said, z sub 2 is not within distance epsilon 1. But if you take any little n that's greater than 2, so little n equals 3, 4, 5, etc., then all of those little n satisfy that that term in the sequence is going to be within the epsilon distance. So z sub 2 itself doesn't need to satisfy that, but z sub anything bigger than 2 would, for that to be a big N. Are there questions or comments thus far? Let's look at another one. I'm going to draw a little smaller epsilon. And make it some epsilon 2. So, Gary, let's look at epsilon 2, which is kind of the smaller distance and gives us this yellow disk centered at z naught. Is z1 going to be contained within that yellow disk?
No.
Is z2?
No.
Is z3?
No.
Is z4?
Yeah.
Is z5?
Yeah.
z6?
Yeah.
z7?
Yeah.
z7 1,000?
Yes.
Assuming I'm not trying to trick you with this drawing and say, aha, I tricked you, z sub 1,000 is way out here, I would say so.
Yeah.
But yeah, so in other words, eventually all the terms in the sequence are going to be within that epsilon 2 disk centered at z naught. It's just the first few terms in this case are not. So here's my question. What's going to be our big N value so that if little n is greater than that big N value, the distance from z sub n to z sub naught is going to be less than epsilon 2, meaning the z sub n is within that epsilon 2 disk.
Would it be n equals 3?
Well, let's take a look. If big N equals 3, is it going to be the case that for any little n greater than 3, so little n equals 4, little n equals 5, little n equals 6, it's within that epsilon 2 neighborhood?
Yeah.
Everyone else agree? I agree as well. Yeah. So the key idea here is there comes a point in the sequence, in this case past the third term in the sequence, where once you get past that third term in the sequence, then the distance from z sub little n to z naught is always going to be less than that epsilon 2. Katrina?
Quick question, in the packet, it says that, for any epsilon greater than 0, there exists an integer, and is that, like, still we're presuming positive integers, or in a
Oh.
complex world could it be?
Let's make it a positive integer.
Okay.
I mean, technically, I guess you could say I don't know, if we picked an epsilon big enough that includes all the terms in the sequence, we could technically say, oh, for all little n greater than 0, this works, or for all little n greater than -5, this technically works. Yeah, that should probably say positive
But
integer.
you still can't have like a sequence of like, I don't know, z sub -5, because like, that's
Well-
just, it's weird,
Not this week.
but eventually perhaps.
Eventually we can, and it'll be a doubly indexed sequence, and that'll get us, that's like week 3 discussion of Laurent series, which is our generalization of Taylor series that has negative powers. But for now, no, we're not going to have that.
Okay.
And when we do, we'll just split it up into 2 sequences, one with positive terms, one with negative terms. Good question, though. Yeah, now the fact that we're dealing with complex numbers as opposed to real numbers, the only real difference in this definition from the one you all saw in real analysis is the fact that the z sub n's and the z naught can be complex numbers. Big N still has to be a positive integer. Little n we're always going to consider to be positive integers. And the picture's going to be a little bit different, looking at points in this sort of plane as opposed to just on like a number line. But the intuition and how it works in practice is essentially just going to be the same. We're not going to have any of these sneaky, weirdly defined sequences with negative coefficients showing up, let's say. So great. Given epsilon 1, we found a big N past which every term in the sequence has distance from z naught less than epsilon 1. Given epsilon 2, we found a big N past which every term in the sequence has distance from z naught less than epsilon 2. In order to prove that the sequence does converge to z naught, which we can denote, I forgot to write this down, as saying the limit as n goes to infinity of z sub n is equal to z naught. In order to formally show that, we have to show that no matter how small an epsilon I give you, you can always find a big N past which every term in the sequence is within that distance epsilon from 0. So, Caleb and Gary, you all just showed that for this epsilon 1, we can find a big N that gets the job done. For this smaller epsilon 2, we can find a big N that gets the job done. But I could always come back and say, aha, I'm an even smaller epsilon 3, or I'm feeling really angry at you. I'm even smaller epsilon 4. What we're going to be working our way towards building up is how can you prove for an arbitrary epsilon as opposed to just some specific one I throw at you. But this is the idea of how you would sort of answer the challenge. If I challenge you with, here's an epsilon, you all need to be able to tell me, oh, well, for the epsilon you just gave me, Dr. Gerstle, here's the big N point past which every term in the sequence is within that distance from z naught. Questions, comments, concerns thus far? So what happens if not every, I'm on page 2 now. What happens if not every epsilon has a big N that corresponds to it? Katrine, what do you think?
I just think it wouldn't converge.
Or it wouldn't converge to Z naught at least. Yeah. So if you were able to find an epsilon for which no big N would get the job done, that would be a sign that the limit as n goes to infinity of Z sub n would be unequal to Z naught. You could have that the limit is some other point, or potentially that the limit just does not exist at all. So let's look at another example. And this time I'll give you all a specific sequence that we can work with. Let's say we wanted to look at the sequence Z sub n is going to be defined to just be equal to straight up I to the nth power. So with that in mind, Caleb, what would Z sub 1 be equal to?
I.
Yeah, Z sub 1 would be equal to I. Gary, how about Z sub 2?
-1.
Yeah, it's going to be I squared, which will be -1. Ginger, Z3?
Would be negative I.
I cubed, which comes out to I squared times I, so negative I. Katrine, Z4?
I to the 4th, which is 1.
Which is I squared squared, so -1 squared, which comes out to a positive 1. Caleb, how about Z sub 5? I am calling on you. Sorry, bad jokes aside. Get I to the 5th, which simplifies to I. Gary, Z to the 6th?
That would be -1.
You take I to the 6th, that's just I times I to the 5th, and I times I is -1. And we're going to keep repeating ourselves. We're going to keep cycling back and forth between I, -1, I, 1, I, -1, I, 1. And as n keeps getting bigger and bigger, our terms are going to keep cycling through those 4 values in the same order forever. So if we were to graph all of these points in the complex plane, what would we end up getting? We would get a point Z1 way up here at I. We would get a point Z2 at -1. So like on the negative real axis. Down here at negative I, we would get Z3. Over here at positive 1, so on the positive real axis, we would get our Z4. And then it would just keep repeating itself forever. We get Z1 is equal to Z5, Z2 is equal to Z6, Z3 is equal to Z7, Z4 is equal to Z8, Z1 is equal to Z9, Z6 is equal to Z10, equals Z11, equals Z12, etc., etc. But we sort of what we're going to end up with is these 4 distinct points in the complex plane that our sequence is kind of hops back and forth between as n gets bigger and bigger, goes to infinity. Here's my question. Does this sequence converge to anything? And if so, what does it converge to? Gary?
I don't think it converges on anything.
You don't think it converges to anything? Why is that?
I mean, it's just going in a circle. It's not really.
Zeroing in on any single number?
No. I don't think so.
Does everyone agree with that? Yeah,
Okay.
I absolutely agree with that. Yeah, no, that's a good way of thinking about it. Like, your sequence is never getting close and staying close to any single number, so it's not possible for the sequence to converge, at least intuitively. Let's show though, for instance, that the limit as n goes to infinity of z sub n is not equal to I. Just for starters. Just so we can kind of talk about how does the definition fail in the case that as n goes to infinity, z sub n is getting close, is converging to I. You're absolutely right, Gary. This sequence doesn't converge to anything. Let's show how it doesn't work at, say, I. So what do we need to do? In order for a sequence to converge, we need to show that given any epsilon whatsoever, there comes a point in the sequence, a big N point, past which every subsequent term is within that epsilon distance from I, if it was to converge to I. But if we want to show that it doesn't converge to I, Ginger, how would we do that?
We would start, I mean, we could just choose an epsilon equal to like 1/2.
Okay. So pick an epsilon equals to 1/2. So that would give us a,
4 to 1 to make it easier, actually.
well, it doesn't really matter.
Okay,
Just make it less than square root of 2 to make it easy.
yeah, okay.
Let's do 1/2. I like 1/2. So let's say here's our epsilon distance right here. Epsilon equals 1/2. So here's my question, Caleb. How far out do we need to go? Do we need to go in the sequence before every subsequent term is within distance 1/2 from I? So in other words, how far out in the sequence do we need to go so that every single term past that point is within this yellow disk I just drew?
It would never happen,
It would never happen. Why is that?
because you're jumping from Z1 to Z2 to Z3 to Z4, and those points would never be inside of that epsilon.
Okay, so why can't we just let big N equals 5 to avoid those 4 points?
It's 5.
Would it be the case that past the 5th point in the sequence, every subsequent point is within that epsilon disk?
No, Z6 wouldn't be.
Okay, what if big N equals 1 billion?
1,000,000,001 equals Z would not be in the interval of the disk.
Actually, a billion one would be, because 1,000,000,001 would be right here.
Oh, 1,000,002.
1,000,002 wouldn't work. Yeah. But in other words, no matter how big a capital N you take, there's always going to be points past that capital N point that are outside of this epsilon neighborhood, right? And we can, so let's write that down. No matter how big an N you choose, there will always be some little n bigger than that, little n greater than that big N, such that the distance from z sub n to z naught, or to I, let's say, in this case, is greater than 1/2, greater than the epsilon value that we set. Or that Ginger said, I should say. So in other words, here's a value of epsilon that I can give you for which you don't have a big N that'll work for it. In order for the sequence to converge, it needs to be the case that no matter how small, no matter what epsilon I give you, as long as I'm giving you some positive number epsilon, you can find a point in the sequence past which it stays within that yellow disk. But here's a value of epsilon for which no value of big N will get the job done. No value of big N will satisfy that every term past that point stays within the yellow epsilon disk. And thus, from that we say that the limit of the sequence can't be I. Because if it was I, then every epsilon should be able to have a big N that gets associated with it. Questions, comments, concerns? Notice that we found one epsilon that doesn't work. That doesn't mean every epsilon is not necessarily going to work. Because like if we had drawn an epsilon that was like neighborhood that was like this big, suddenly every single term in the sequence is going to be within that epsilon distance from I. Meaning every term in the sequence is going to be within this huge disk. So for that value of epsilon, we can find a big N that would work. Any big N really. Big N equals 1. Past the first term in the sequence, every term in the sequence is within this big disk. So for some epsilons, you could potentially still find big N's that work. But in order for the sequence to converge, it has to be the case that for every epsilon I throw at you, you can find a big N that would work. And in this case, you can find a big N that works for some epsilons, but some epsilons, like epsilon equals 1/2, won't have any big N's that work for them. Y'all doing okay? Let's do it. So this kind of is how you would show that a sequence fails to converge. Let's look at an algebraic example where we show that a sequence does converge. Let's look at the sequence z sub n is equal to I over 2 to the n minus I. I claim the sequence converges, and I think we can actually prove that. Ginger, what do you think the sequence would converge to?
Probably negative 5,
Why negative I?
because I can see the first term going to 0.
So you're basically saying as n gets bigger and bigger, this term gets really, really close to 0 and basically becomes inconsequential?
Yeah.
I see. Interesting. Yeah. Intuitively, this term is going to go to 0. The negative I term doesn't care what n is doing. And so the whole thing would go to negative I. So according to Ginger's claim, z sub n should converge to negative I. So let's see if we can actually prove that algebraically. In other words, construct a formal proof that no matter what epsilon I give you, you can always find a big N past which every term in this sequence has distance from negative I that's less than that epsilon. So Katrine, based on your experience working with sequences and real analysis, where would you suggest we should start?
I think we should do some scratch work and find a big N in terms of epsilon.
Yeah, I agree. So before we start trying to get all gung-ho and write a formal proof that for every epsilon we can find a big N that will do blah, 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 we need to do a little bit of scratch work on the side first before we start writing our formal proof. And the goal of the scratch work is going to be to ask the question of given some epsilon, how can we find a big N for that epsilon show that if little n is greater than big N, then the distance from z sub n to that z sub naught has to be less than epsilon. So we need to answer the question of, if I were to give you some epsilon, how do you go about finding a big N that'll get the job done for that epsilon? So Ginger, how would you suggest we go about finding, approaching this scratch work?
I don't remember at all how to do this.
My goodness, you need to take back your analysis grade then.
Okay, sounds good.
So in general, so Katrine, how would you start off the scratch work?
I would take the z sub n minus z sub naught, and I would plug in what we have. So we would get like 1 over 2 to the n minus I minus negative I is less than epsilon.
Yeah, so in other words, we want this expression to be less than epsilon. We need to see what condition does n need to satisfy for this distance, the distance from z sub n to little z naught, to be less than epsilon. Let's look at this expression. Plug in the limit that we have, or the limit that we claim should work, and see what it comes out to. So Caleb, what would z sub n be in this case? So how, in other words, how did we define the nth term in the sequence?
Oh, 1 over z to the n minus I, 2 to the n minus
I over 2 to the n
I?
minus I.
Yeah, okay.
Yeah, the z sub n, yeah. Let's say, yeah, maybe I can draw that a little better. That's supposed to be a dot for the I. So yeah, so the nth term in our sequence is just going to be I over 2 to the n minus I. And Gary, what's going to be our z naught? In other words, what's the value that Ginger claimed the sequence is going to converge to?
Negative I.
Yeah, so we need to subtract off then from that negative I. So z sub n is just the nth term in the sequence, which is usually going to be some expression in terms of n. Z naught is going to refer to what are we claiming that the sequence converges to. And so if we look at that, we get I over 2 to the n minus I minus a negative I. Alright, let's do some algebra here. This is going to come out to I over 2 to the n minus I plus I, absolute value of all of that. Caleb, anything we can do to simplify this?
Negative I plus I.
What?
0.
Oh, in those little swoosh swoosh. Just get absolute value of I over 2 to the n. Where can we go from here? Get the video still going.
That's always positive.
What's always positive?
I over 2 to the n.
I over 2 to the n is always positive.
Yeah.
I agree 2 to the n is positive. How is I? I mean,
Oh, I guess we can't say a complex number is positive.
man, that was our day one.
Yeah.
We don't have a nice way of saying what does it mean for something to be, for one complex number to be greater than or less than another one. I do think you're on the right track though. Ish. Remember on homework 1 you all proved that absolute value breaks up nicely over products?
Mhm.
Same idea you can use to say that it breaks up nicely over quotients as well. Meaning we could break this up into absolute value of I over the absolute value of 2 to the n. So Ginger, what's the absolute value of 2 to the n?
2 to the n.
Yeah. 2 to the n is going to be some positive real number, so it will equal its own absolute value. What's the absolute value of I?
1.
Yeah. So absolute value of I over absolute value of 2 to the n is just going to come out to 1 divided by 2 to the n.
Why is the absolute value of I 1?
Yeah.
Andrew, how'd you get 1?
It's the magnitude, so it's like the square root of I squared plus 0 squared. Yeah.
Yeah, because you could write it out as 0 plus 1 times I, which is going to give you 0 squared plus 1 squared, which comes out to 1. Or if you just look at where does I lie in the complex plane, absolute value is just distance from the origin. This point's going to have a distance of 1 from the origin in the complex plane. Yeah. Point is, I is just a constant. Any constant complex number is something that we should be able to just take the absolute value of using our day 1 formula. All right, neato burrito. So, what do we need? Oh, I shouldn't have erased the definition of convergence. Whatever. I had it from goal. So we know that the nth term in our sequence is always going to have a distance from our claimed limit of negative I, or z naught. The distance from z sub n to z naught is always just going to be equal to 1 over 2 to the n. So as part of our scratch work, what do we need? We're going to need that 1 over 2 to the n has to be less than epsilon as part of our eventual proof. So the question's going to become, how big does little n need to be for 1 over little 2 to the n to be less than epsilon? Because that's our goal. We need to find a point in the sequence past which this expression comes out to less than epsilon. So how can we find a value of little n that satisfies that? Let me ask you this. Picking on these two a lot because they've seen a lot of these sorts of examples in real analysis last semester. I'll pick on you all more once you get a little more practice with this. Katrine, how would you determine the value of little n that would satisfy that? Or maybe another way to ask that is, how would you solve that inequality for little n?
I mean, you could multiply both sides by 2 to the n.
Cool. So it was 1 less than epsilon times 2 to the n.
Yeah, and then divide both sides by epsilon.
Okay, that'll give us 1 over epsilon is less than 2 to the little n.
And then I think you're going to have to do something with a log in order to take the n down.
Ah, something with a log.
Take the log base 2 of both sides, I think.
I think so. And here we're just talking about the standard logarithm you've seen before. 1 over epsilon and 2 to the n are both just going to be positive real numbers. So that's going to tell us that log base 2 of 1 over epsilon is going to have to be less than log base 2 of 2 to the n. But Caleb, what's log base 2 of 2 to the n going to be?
N?
Yeah, that by definition is just going to be n. So how big does little n need to be in order to make that happen, in order to make this work out? Little n just needs to be strictly greater than log base 2 of 1 over epsilon. And that is what we needed from all of our scratch work. We needed to be able to say, if we're given some epsilon, how can we find a how far out we need to go in the sequence in order to guarantee that the distance from z sub little n to z naught is less than that epsilon. Turns out we need to go past the log base 2 of 1 over epsilon term in the sequence in order to guarantee distance from z sub n to z naught is less than epsilon. June, do you have a question?
Well, but maybe I'm remembering this wrong, but didn't we wanna find a big N?
We do. So, alright, how would you choose a big N?
Oh yeah, you have to do like the ceiling of that number along base 2 of 1 over e.
Something like this?
Yeah.
Yeah. I think that'll get the job done. Katrine, what's the ceiling of a number?
We're basically just rounding it up to the next whole number.
Yeah, we're rounding it up to the next, biggest integer in general. So, here's the problem. We could try and let big N be equal to log base 2 of 1 over epsilon, but we can't necessarily do that because big N has to be a natural number, and there's no guarantee that log base 2 of 1 over epsilon is going to be a natural number or a positive integer. So in order to guarantee big N is a positive integer while still doing what we want it to, we can just say round log base 2 of 1 over epsilon up to the nearest whole number. Nearest integer. If it's not already an integer, just round it up so that it becomes 1. So if it's something like 2.6, round it up to 3. Something like that. So far, so good? Caleb, you look like you have something you want to ask.
So what if there's an epsilon value that's smaller than, or an n that's smaller than the log base 2 of 1 over e?
Well, then you just don't want to, you want to make sure your little n doesn't include that. Something to keep in mind is, as part of our proof, we're going to assume that little n is greater than big N. We're going to be saying, let's only look at terms in the sequence that are past whatever term that is. So that comes out to 3, for instance. We're going to say, look at values of little n that come past the third term in our sequence. And if you remember back to what we were doing on the front page, given some epsilon, our main goal was to say, find a point in the sequence past which every term in the sequence is within distance epsilon from z naught. And if this expression came out to 3, then we could just say, oh, okay, little n just needs to be greater than the third term in the sequence.
And then we would know what converges.
Say what?
Then we would know what converges.
Bingo. Yeah, we would. So I think what we're ready to do now is we're ready to actually write a formal proof that kind of sums up everything we've said so far. Sound good to everyone? Gary, doing all right? All right, let's write our proof. So here's our proof. And again, this is a proof that the limit as n goes to infinity of z sub n is equal to z naught for this z sub n and this z naught. All right, let's see, who do I want to ask to start this? Ginger, how would we start off our proof?
Let epsilon be greater.
Actually, you know what, I don't want to ask you. I have Lincoln across the hall, I'm going to get him in on this.
I knew that was gonna happen.
I did too. I was really thinking about that.
Yeah, me too.
What are the odds you guys are just like,
We don't know how to start off a particular proof. So Lincoln, we have a sequence that we're trying to claim converges to some particular number, and we need your help in starting off our proof.
Poor Lincoln.
let epsilon be greater than 0.
Alright, let epsilon be greater than 0. Thanks, Lincoln. So, Lincoln was in my real analysis class too last semester, and he was the designated person to always say, let epsilon be greater than 0 to start off our proofs. So I had to drag him in for one last hurrah. But yeah, so the way one of these sequence convergence proofs, and later on function convergence proofs, is going to start is you're going to let epsilon be greater than 0, which means I'm going to pick some epsilon which I'm going to work with. Unlike what we did in the front page, where we had, or the front 2 pages, where we would say like, oh, let's look at epsilon equals 1/2, or let's look at epsilon equals this thing I just drew on the board. We're not going to assume anything about epsilon other than that it's positive. It's a positive real number. But specifically, if all that we're assuming about epsilon is that it's greater than 0, then epsilon could theoretically represent any number greater than 0.
So it could be infinitesimally small.
It could be. Well, infinitesimally, arbitrarily small, let's say. Infinitesimally has its own kind of baggage attached to it.
Yeah.
Sorry. Could epsilon be an imaginary number?
Nope.
Okay.
Epsilon is still has to be a positive real number because epsilon refers to sort of distance from z sub n to z sub naught. And whenever we're talking about distances in the complex plane, our distances we still want to be positive real numbers, just like it was last semester. Good question. You can do something. No, I'm not going to get into that. All right, we've picked an arbitrary epsilon. Our second step in the proof is always going to be define your big N that you claim is going to get the job done. In other words, pick a big N that you claim if little n is greater than big N, then the nth term in your sequence has to be distance from z naught less than that epsilon you started with. So in this case, Katrine, what was our big N?
The ceiling of log base 2 of 1 over epsilon.
So let's let big N be equal to the ceiling, so rounding up, log base 2 of 1 over epsilon. And now, what we need to do is we need to show that if little n is greater than big N, then the distance from z sub n to z naught is less than epsilon. And if we can do that, then that would complete our proof. So let's assume that we have some little n greater than this big N. And look at absolute value of z sub n minus z naught. So Caleb, what is the distance from z sub little n to z naught? Or I guess what's our z sub little n and what was our z to z naught?
Oh, was it I over 2n
I over 2 to the n
minus I
minus I, and then what was our z naught?
minus I?
Yeah, so we plug that in here, we get this expression. I over 2 to the n minus I minus negative I. And then what we're going to end up having to do is basically repeat a lot of the algebra that we did in our scratch work over here. So we can say that's going to simplify to just absolute value of I over 2 to the n, which is equal to absolute value of I over absolute value of 2 to the n, which is equal to 1 over 2 to the n. So far, just kind of repeating what we did in our scratch work when we were looking originally at our z sub n minus z naught expression. Katrine, what can we say about 1 over 2 to the little n?
You know that it has to be less than 1 over 2 to the big N because n is bigger than big N.
Yeah, we can use the fact that little n is greater than big N to say that 1 over 2 to the little n is going to be less than 1 over 2 to the big N. Here we're relying on the fact that 2 to the little n is going to be greater than 2 to the big N, which means 1 over 2 to the little n is less than 1 over 2 to the big N. And that if you have two fractions with the same numerator, then whichever one has the smaller denominator is the greater fraction. That sound good to everyone? Caleb?
Yeah.
I'm not convinced by your facial expressions. So we're assuming little n is greater than big N, right?
Yes.
Would you agree that means 2 to the little n is greater than 2 to the big N?
Yeah. Yeah. Oh, and then 1 over means we flip the inequality.
Yeah, if you take the reciprocal on both sides, then the inequality flips. It's sort of like 2 is less than 3, but 1/2 is greater than 1/3. Like the smaller the denominator in general, the bigger your fraction is. And the bigger your denominator, the smaller the overall fraction is. So that's kind of what's going on here. All right, so we have 1 over 2 to the big N showing up. Ginger, how can we relate that back to epsilon somehow?
So since big N is the ceiling of log base 2 of 1 over epsilon, we know that big N is always going to be greater than or equal to the log base 2 of 1 over epsilon.
I agree with that.
So if we take that over to our fraction, then we can say 1 over 2 to the big N is going to be less than or equal to 1 over 2 to the log base 2 of 1 over epsilon.
Indeed. Yeah, that's absolutely right. We can use the fact that big N is greater than or equal to log base 2 of 1 over epsilon. And that's just from how we originally defined our big N. We said take log base 2 of 1 over epsilon and round it up to the nearest integer. Well, if we're rounding it up, it's going to be getting bigger or stay the same size. So big N will be greater than or equal to that. And then that means 1 over 2 to the big N is going to have to be less than or equal to 1 over 2 to the value of expression that's smaller than big N. So far, so good. Gary, what's 2 to the power of log base 2 of 1 over epsilon? In other words, how can we simplify it? 2 to the power of log base 2 of blah.
I'm not entirely sure, actually.
Yeah. Exponentials and logs are not the most comfortable
I
thing.
haven't seen that in a while.
So, let me ask you this. 2 to the log base 2 of x in general is saying, I need to take 2 to the power of the thing that 2 to the power of that thing is equal to x. Okay, that didn't come out quite as intuitive as I would have liked. 2. So in general, here, let's look at this one. This is saying I need to take log base 2 of 2 to the x. That would be saying 2 to what power is going to be equal to 2 to the x?
Okay.
So answer me
So
this.
it would just be x, right?
Yeah, this one comes out to x.
So that would just be 1 over epsilon, right?
Yep.
Okay. So just
For similar reasons, this will come out to x.
Okay. Yeah.
Phrasing in terms of this I found is less intuitive than phrasing it like that.
No,
But the idea is 2 to the x and log base 2 of x are inverses of each other. They cancel each other out in either order. So in this case, 2 to the log base 2 of 1 over epsilon is just going to come out to 1 over epsilon. And Caleb, what's 1 over epsilon going to equal?
Epsilon. What is less than or equal to 1 over 2 to the log base 2?
The 1 over 2 to the big N. thing in the line above it. And that was coming from the fact that log base 2 of 1 over epsilon is itself less than or equal to big N.
You said it was greater than, or no, oh, it's less than n.
Big N is greater than or equal to that,
Oh, yeah.
which means 2 to that is greater than or equal to 2 to that, which means 1 over 2 to the big N will be, you're taking the reciprocal of both sides again, the inequality flips. To give you 1 over 2 to the big N is less than or equal to 1 over 2 to the, what is 2 to 1?
And where do we establish that n is greater than or equal to log base 2 of 1 over epsilon?
Right when we define big N. When we define big N to be, take log base 2 of 1 over epsilon, round it up to the nearest integer. Because if we're rounding log base 2 of 1 over epsilon up to get N, then by definition that means N has to be, if log base 2 of 1 over epsilon is already an integer, then big N will be equal to it. If this isn't already an integer, then when we round it up, to get big N will be strictly greater than it.
It's greater than or equal to.
Hence the greater than or equal to, where whether it's greater than or whether it's equal to depends on when we did our rounding, did we actually have to do any rounding or was it already an integer? So far so good? So Ginger, what did we just show? We showed that the distance from z sub n to z naught is equal to thing, is equal to thing, is equal to thing, is equal to thing, is strictly less than thing, is less than or equal to thing, is equal to thing, is equal to epsilon.
We showed that the first thing is strictly less than the last thing.
Yeah, exactly. Through our string of inequalities, what we were able to show is thus the distance from z sub n to z sub naught is strictly smaller than epsilon. From the fact that we have a string of equalities and inequalities starting at z sub n minus z naught, ending at epsilon, and in between we only had equal to signs, a strictly less than sign, and a strictly less, and a less than or equal to along the way. The fact that we didn't have any greater thans or greater than or equal to's mixed in means first term had to have been strictly less than the last term. So Katrine, what did we just prove? We showed that given an arbitrary epsilon greater than 0, we were able to find a big N so that if little n is greater than that big N, then the distance from z sub little n to z naught is less than epsilon. What does that give us?
We've shown that z sub n converges to negative I.
Yeah. Thus, by definition, the limit as n goes to infinity of z sub n is equal to z naught. In other words, limit as n goes to infinity of I over 2 to the n minus I is equal to negative I. And there's our proof. So the goal of the scratch work was to find how can we write big N as an expression in terms of epsilon, just so that when we started writing out our formal proof, we could include that right at the start and say, we've picked an epsilon, now we can choose the big N that our scratch work told us was going to work. And then after you've picked your big N and let little n be greater than that, then the rest of the proof is just basically showing what your scratch work did, that the big N you chose, in fact, does work for the epsilon you started with. And the beauty of this proof is that epsilon could be anything. Epsilon could be 5, epsilon could be 1/2, epsilon could be 1 over a trillion. We didn't specify a specific value for epsilon, other than that it had to be greater than 0. So no matter what epsilon, specific epsilon we have in mind, this proof would show that if I give you an epsilon, you can find a big N that works for that epsilon. Meaning if I give you any epsilon, you can find a big N, so that past that big Nth term in the sequence, every subsequent term is within distance epsilon from the Z naught we started with. Questions, comments, concerns? Hey, I think it's a good time for our first break then. So let's come back at 10:22. And when we come back, we'll talk about how we can take these ideas related to sequence convergence and do something which I'm a little bit more interested in going forward. How can we show that a function has a particular limit at a point, as opposed to just a sequence of points? Which will be pretty similar, but with a slight twist to it. So we'll be back in 10 minutes. Have fun in the meantime. Hi Sarah, I hope all is going well. Feel free to skip a few minutes ahead in the video. Doing okay?
Yeah.
It's pretty intense, and we're going through this fairly quickly.
Yeah.
I mean, I realize that, so I'd say Ginger and Katrina have done plenty of these proofs. I know you and Gary have not, so
Yeah.
it's
I haven't taken real analysis yet.
yeah. Well, benefit is once you do, when you start seeing all these proofs, you'll have some more experience with it.
That's true. Yep.
And these sort of proofs have kind of a natural flow in that, like the first couple that you do, they're really scary and tough, but they're all kind of have essentially the same structure to them. You pick an epsilon, you pick a big N based on your epsilon, then if little n's greater than big N, you show epsilon times Z, you show that. And once you kind of do a couple of them, I think it starts becoming a little bit easier, because you kind of get used to the whole strategy that you're working with. That's how it was for me, at least.
Right, yeah.
First, I was pretty intimidated too. Yeah.
found this thing called God's number, which apparently on a 3x3, once you apply like 18 moves on it, it doesn't scramble the cube any further, it just reorients the pieces.
Oh.
And out of like the 43 like quintillion possibilities,
Yeah.
it could technically be solved in 18 moves no matter what, but a person can't really like figure it out that way.
And there's a lot of cool theory behind like looking at the Rubik's Cube and permutation theory. I've talked a little bit about it in doing abstract algebra before.
Unbelievable.
That's so
That's
insane.
unbelievable.
That's quite impressive. Well, I'll give a round of applause for that.
It's like my most random like skill I have.
How long did it take you to get before you could do that?
Well, to do it that fast, it's just take me probably like 3-4 years.
Oh, okay.
Yeah.
I
but-
say,
you know what inspired me? There was this 7th grader that I saw that literally can do it in like 10 seconds. And I was like, that is unbelievable. So I was like, right after school, I was like, I'm gonna go to Target, just buy Rubik's Cube, and just try to figure out how to solve this thing. And then from there, it's just a rabbit hole. I just got addicted to it.
nice.
Yeah.
Yeah, my sister learned how to solve one, and she's like showing it off at Christmas time. It usually takes her a good 45 seconds to a minute.
Mhm.
I think you've got her beat.
Yeah, it's a lot of fun though.
It's not something I've ever tried to learn myself, but it's there is a lot of cool mathematical theory behind it.
It is, yeah.
Alrighty. Oh, you missed Gary showing off his skills. It's the Rubik's Cube. Alrighty, so let's get back to it. So what we're going to be focusing on for kind of the rest of today's class is instead of looking now at how sequences converge using sort of this epsilon definition, we're going to come up with an epsilon definition for what it means for a function to converge at a point. Meaning asking the question of like, if we take a limit as z approaches some fixed point z naught, what's going to be the limit of f of z? And it turns out we can have a similar sort of definition for functions. That we can say, given a complex f of z, the limit of f of z as z goes to z naught, which we're going to denoted by limit as z approaches z naught of f of z equals L, is the number L satisfying that for all epsilon greater than 0, there exists delta greater than 0 such that if 0 is less than the distance from z to z naught is less than delta, then the distance from f of z to L has to be less than epsilon. So for all epsilon, there exists a delta such that if the distance from z to z naught is less than delta, then the distance from f of z to L is going to be less than epsilon. Yes.
So is delta, I'm just thinking like graphically, would that be like a disk similar to epsilon?
Yeah, so let's try and graph the picture to see what's going on here. So the idea is we have some point z naught, and we want to show that the limit as z approaches z naught is going to be equal to some value L. Let's say L's out here somewhere. And F is mapping kind of one copy of the complex plane to another copy of the complex plane. The key idea in this case is that if I was to set any epsilon distance around L out here, so let's say if I set an epsilon 1 out here, it needs to be the case that I can draw out some delta 1 neighborhood in the original copy of the complex plane around Z0. Let's say it looks something like this. So that everything in the delta neighborhood of Z0 has to map to points that are within our epsilon neighborhood of L. So that given any epsilon neighborhood of L, there exists some delta neighborhood of Z0 that maps entirely inside of it. Delta here is kind of playing an analogous role to what capital N did in the sequence convergence definition. And that when we're looking at a sequence where we're just having this kind of like discrete set of points that we're looking at, we were saying that if we drew any epsilon disk around what we claimed our limit of the sequence is, all the points in the sequence had to eventually be inside of it. Here, where we're looking at two copies of the complex plane, it's going to be slightly different in that we're still going to be drawing an epsilon disk around our limiting point in kind of our codomain and the points that are getting mapped to in the complex plane. But the key difference here is that we have to go back to the original domain where Z0 is located, and we're going to have to draw another disk centered at Z0. That'll be our delta neighborhood, our delta disk, so that all the points in our delta disk here have to map to within our epsilon disk over here in order for the limit as Z approaches Z0 of our function to be equal to L. Just like with sequence convergence, we have to be able to do this for any epsilon. So if I gave you this epsilon, this fairly large disk around L, you could probably have a fairly large disk around Z0 that's going to map inside of it. But if I had given you, say, some smaller epsilon, let's say some yellow epsilon 2 disk that's smaller than our epsilon 1 disk, Katrine, what's probably going to have to be true about our corresponding delta 2 disk over here? Is it probably going to be smaller or bigger than the delta 1 disk?
It's probably also going to be smaller.
It's probably also going to be smaller, yeah. Corresponding to the fact that what we're saying is that if I gave you an epsilon 1, maybe you could say, oh, all of these points that are vaguely close to Z0 are going to map to within that epsilon 1 neighborhood. Now when we go to a smaller epsilon 2, I'm saying, all right, I'm tightening the bounds. I'm now saying you need to get really, really close to L when you're plugging in values of Z into your function. So what that probably means is that you're going to need even closer values of Z to Z0 over here, so that values within this yellow disk map to values of Z within that yellow disk. And the key idea is no matter how small an epsilon neighborhood over here I give you, even if I give you one that's like super, super small, you should always be able to find a super, super small delta neighborhood of Z0 so that all the points in the disk over here in the domain map to points within distance epsilon, so in this smaller and smaller disk over here. And that's sort of the key idea behind what's going on, is that we have, if I give you a disk centered at L, you need to be able to give me a corresponding disk centered at Z naught that maps to within it. Any questions or comments about that before we start looking at some specific examples? So if we go to the next page for a second. Let's say we wanted to look at the function f of z equals z squared at z naught equals 0. So we're going to have two copies of the complex plane, one for the inputs, one for the outputs to the function f. Our z naught is going to be located at the origin. And let's see. Ginger, what do you think that the limit of this function is going to be? As z gets closer and closer to 0, what do you think z squared is going to get closer and closer to?
0.
You think it's going to just be 0 squared or 0?
Yeah.
Probably is. Let's say for the sake of argument, I disagree with you, Ginger, and I think that the limit's going to be 1. I'll put an L question mark because I don't feel very confident in that. So let me ask you this. If I were to draw some epsilon neighborhood around 1 here, is it possible, Gary, to find some delta neighborhood around the origin over here, so that if we take any point in our delta neighborhood here, every point within that delta neighborhood is going to map to points within that epsilon neighborhood over here?
No.
No matter how, I can't make a teeny tiny delta neighborhood that'll map to within anything?
No.
Yeah, I agree, you can't do it.
Yeah.
The idea being, no matter how small a delta neighborhood I draw over here, I'm always going to get points that are really close to 0, right? If we're looking at values of z that are really, really, really close to 0, if we plug that into the function f of z equals z squared, what are the outputs going to be really, really close to?
Sorry, did you ask me what that again?
Yes.
I was right.
Yes, I'm sorry. If we're plugging in values of z with it that are really, really close to z naught of 0 here, if we're plugging those into the function here, values of z that are really close to 0, what are the outputs going to be really, really close to?
It should be close to 0 also.
Yeah, they're going to be really, really close to 0 as well. Is that bin out there right here? And if they're really, really close to 0, then for this epsilon neighborhood I just drew, or the x points I just marked, Caleb, within the epsilon neighborhood or outside of it?
They're outside of it.
They're outside of it. So what does that mean? That would tell us that given this epsilon neighborhood, let's say epsilon equals 1/2, for instance. So we know 0 is not included in it. So given epsilon equals 1/2, I would say, in this picture, no matter how small a delta neighborhood we draw around z naught equals 0 in our original picture, there will be points within that delta neighborhood mapping to outside of our epsilon neighborhood. Of L equals 1. So Katrine, what does that tell us? If we can find an epsilon neighborhood of 1 here, so that no matter how small a delta neighborhood we draw around 0, we're always going to get points that map outside of the epsilon neighborhood over there.
F of z doesn't converge to 1.
Yeah. In other words, we can say that the limit as z approaches 0 of our function f of z can't possibly be equal to 1. If the limit was 1, then given any epsilon neighborhood, including this epsilon equals a half neighborhood, we should be able to find some neighborhood around 0 here that maps entirely inside of it. And it could be the case that there's some points within our delta neighborhood that map within the epsilon neighborhood. But the point is, in order for the limit to be 1, it would have to be the case that for some delta neighborhood, every point in our delta neighborhood would have to map to within our epsilon neighborhood.
Was choosing L equals 1 purely arbitrary?
That was arbitrary, well, arbitrary in the sense that I knew it wasn't the actual limit.
So you're just trying to show that this is why it's not the limit?
Yeah.
Oh, okay.
If we had tried to repeat this process at 0, the actual limit, according to Ginger, we would have found that given any epsilon, we could find a delta neighborhood that does map within it.
Okay.
But yeah, me picking 1 here is just like was somewhat arbitrary, just to show that like, hey, here's a point that the limit can't be because of these reasons right here.
And what is Z not? Is that like what the limit is supposedly approaching?
Yeah, that's the value that Z is going to be approaching, that the inputs are approaching. So over here, it's if we want to say that the limit is Z approaches Z naught of our function is L,
Oh, yeah.
Z naught is where we're centering our delta neighborhoods, L is where we're going to be centering our epsilon neighborhoods.
Which are our outputs?
Yes, correct. Yeah, the epsilon neighborhoods always correspond to where the outputs live. The delta neighborhoods are always going to correspond to where the inputs end up living. Yeah, good questions. Anybody else? I have a question then. If we look back at our definition, we technically didn't say for all epsilon there exists a delta such that if the distance from z to z naught is less than delta, the distance from f of z to L is less than epsilon. We said that as long as the distance from z to z naught is less than delta, but also greater than 0, then the distance from f of z has to be less to L has to be less than epsilon. So in other words, we're saying we don't care about what happens if the distance from z to z naught is equal to 0. Why is that, do you think? Why do you think we have this extra 0 less than condition here? Katrine?
Well, there could be like a hole at that point, like at 0 or at wherever we're trying to approach, and the limit could still exist, even if like the actual point is satisfied.
Is doing something weird there? Yeah, because that's the idea of like what's happening when we're taking a limit. So Gary, if we want to take a limit as z approaches 0 of some function, do we care about what happens at the point 0 itself?
No, just care what happens around it.
Yeah, we care what happens at all the points close by, but at 0 itself, the limit is unaffected. So like that's what allows us to take, for instance, the limit as z goes to 0 of z over z. At z equals 0 itself, this expression's undefined.
Isn't it 1?
Nope, not at z equals 0. It's 1 everywhere else except 0. But at 0 itself, it's undefined.
What about L'Hopital's rule?
The limit exists. The limit is 1, but the function f of z
Oh.
equals z over z itself is undefined at 0. So yeah. So in this case, what we'd basically be saying is, hey, let's take a look at let's take a look at what this would look like in the complex plane. Basically, we'd be saying, no matter what values of z you're plugging in to this function, you're always going to get outputs that are exactly at 1 itself. The only problem is you can't plug 0 itself into this function because the function's undefined here. But you can still say that the limit would be 1, because if you, I don't know, pick any epsilon neighborhood of 1, then really any delta neighborhood of 0 would satisfy that any points within this delta neighborhood of 0 are all going to map to within this epsilon neighborhood of 1,
Including 0 even though it's undefined, right?
except at 0.
Oh.
Every point in this delta neighborhood is going to map to 1 exactly, and thus to points within our epsilon neighborhood. 0 itself doesn't map anywhere. This function does not exist at z equals 0. But you can still say that the limit is going to be 1 because everything in your delta neighborhood, other than what happens at the point itself, is going to map to within the epsilon neighborhood. And if we go over here, look at this condition, we only care about points in our delta neighborhood of z naught mapping to within the epsilon neighborhood. We don't care about z naught itself. We just need all other points in our delta neighborhood to map to within that epsilon neighborhood. So the fact that 0 itself doesn't map to within the epsilon neighborhood doesn't really matter. Another way we could think about it is if we had done something like this. F of z equals 1 if z is not equal to 0, 100 if z is equal to 0. So that would be a function where all these points close to 0 would map to 1 exactly. 0 itself maps way over here. But you could still say that the limit would be 1 as z approaches 0, because we just need every point in our delta neighborhood of 0, other than 0 itself, to map to within our epsilon neighborhood of 1. Does that sort of make sense? It's weird, but we're kind of excluding these edge cases where the behavior of the function is different at the point itself than it is nearby. And that's going to lead us to a discussion of continuity here in a little bit. So like these would be functions, for instance, that are not continuous at 0, but the limit is still defined there. So, y'all doing okay? Let's do an example then, where we'll do like what we did with our sequence and actually construct a proof for a particular function. And what I'm going to do is I want to show that the limit as z approaches 3 minus 2i of the function 5z minus 1 plus I is going to be equal to 14 minus 11i. So if we go to 14 minus 11i, we'll get a point that's like down here. That's going to be our L value. Z3 minus 2i is going to be our Z naught value, so that'll be like over here. And what our goal is going to be is to prove that if I give you any epsilon neighborhood of L over here, you can find a delta neighborhood of this point Z naught that'll map to within it. So in other words, our goal is, if I give you an epsilon neighborhood of L, construct a delta neighborhood of Z naught that everything in that delta neighborhood will map to within the epsilon neighborhood. Question, Katrine, do you expect there'll be any issues at the point Z naught equals 3 minus 2i itself here? I don't think so either. Because this looks like a nice continuous thing, and it's a linear function. So it'll probably be okay at z naught itself, unlike the z over z or the f of z I drew over there. So let's see if we can do a proof of this. Ginger, where would you recommend we start?
Could we let epsilon be greater than 0?
Oh,
Oh, wait, no, we should do
For-
scratch word.
I was gonna say, you want to go right into the proof, huh?
No, I don't.
Just like how with our sequence proof, we did some scratch work first to find what's our big N that's going to get the job done. We should probably do some scratch work here to say what value of delta will get the job done for an arbitrary epsilon. So let's do that first. And then yes, our actual proof will start with letting epsilon be greater than 0. So our scratch work is going to have a goal of saying given some epsilon greater than 0, how can we find a delta greater than 0 so that if the distance from z to z naught is between 0 and delta, then the distance from f of z to L will be less than epsilon. And we need to do some scratch work to kind of determine that. In other words, if I gave you an arbitrary epsilon, how can you pick a delta in terms of that epsilon that'll get the job done, that'll work, so to speak? So let's do that. So, y'all doing okay?
Let's have another joke.
Is it time for another joke? Okay. Where's? Oh, yeah. What do you call an angle that's been in an accident? You call it a rectangle.
Nice. Get wrecked.
Get wrecked. Get rectangle. All right, so let's do some scratch work here.
That was good. That was good timing.
Thank you. Oh goodness. So we're going to be assuming, as part of our proof and as part of our scratch work, this condition right here, that the distance from z to z naught is less than delta. What's our z naught here in this proof?
3 minus 2i.
Yeah, 3 minus 2i. Z naught always refers to the point in the domain, in the inputs, that your z values are approaching. So in this case, z is approaching 3 minus 2i. So as part of our proof, we're going to be assuming that the distance from z to 3 minus 2i is going to be less than delta. And what I want to do is I want to look at this expression, the distance from f of z to L. Gary, what's going to be our f of z in this problem? In other words, the function that we're plugging values into.
Would it be the 14 minus 11i?
I don't think that's going to be our function.
Sorry, that's the L. Sorry.
Yeah, that's our L. That's the constant that we're assuming our function converges to.
5z minus 1 plus I.
That piece?
Yeah.
Yeah, I think that's going to be our function. That's like the function that we're actually going to be plugging in values of z into. So we want to show that if we look at points that are close to 3 minus 2i, if we plug them into z here, we want to show that we get outputs that are really close to 14 minus 11i, our L value. So our f of z is 5z minus 1 plus I. Caleb, what's our L value going to represent? The constant that we're claiming is the limit of the function.
3 minus 2i?
No, that's our Z naught. That's the value that the inputs, our delta neighborhoods are gonna be centered at. Where are our epsilon neighborhoods gonna be centered at?
14 minus 11i.
Yeah, I think that's gonna be the L value in this case, is the 14 minus 11i, where,
That's what we're expecting the limit to be?
Mhm.
Oh, because we plugged in Z or 3 minus 2i for Z.
yeah,
And we just solved that algebraically, that's what we got for L.
it would be.
Yeah.
So
Okay.
it turns out in this case that f of 3 minus 2i would be equal to 14 minus 11i. But that's not quite the same as saying that the limit is going to be 14 minus 11i, that all the points close to 3 minus 2i will net to outputs that are close to 14 minus 11i. So to do that, that takes a little bit more work. But yeah, you're right though, that our L value is going to be 14 minus 11i. Oh goodness, ain't this a lovely looking expression? Let's see if we can simplify this. It's going to come out to 5z minus 1 minus I minus 14 plus 11i. Can we simplify that at all, Katrine?
Yes.
What does that simplify to?
5z minus 15 plus 10i.
Okay. Yeah, so that'll simplify to 5z minus 15 plus 10i. It'd be nice if we could somehow relate this expression to our z minus z naught expression. Is there anything we can factor out, Gary, from 5z minus 15 plus 10i? Any constants?
Yeah, we can factor out the Z.
I don't think we can factor out z because we don't have, because not all of these terms have z's attached to them. But are there any common factors that 5z, 15, or negative 15 and 10i all have in common?
I guess.
Not I, because
So it'd just be 5 then.
yeah, 5 I think, because all of these have a factor of 5 that we could kind of pull out.
I'm so used to looking for like eyes and stuff to factor out. Actually,
Yeah.
the fact that it's just a 5.
That's almost a trick question in how simple it is. Yeah, there's a 5 here that we could factor out. And if we factor out 5, what are we going to be left with?
Z minus 3 plus 2i.
Z minus 3 plus 2i. Or in other words, we could write that as being 5 times absolute value of z minus the quantity 3 minus 2i. What do we know about this expression? Or using our assumption up here, what can we assume has to be true about this expression? Kendra?
Can we say it's less than 5 delta?
Less than 5 delta. Oh hey, this expression right here we're assuming is less than delta. So if we have 5 times that, we can assume that is going to be less than 5 times delta. Well, what do you know? So where does that leave us? Well, first of all, before we move on, I should ask, is everyone okay with the algebra here so far? Taking distance from f of z to L, and it turns out that's going to be less than 5 delta, using our starting assumption that the distance from z to z naught is less than delta.
Where do we get the absolute value of f of z minus L? Why are we doing that?
Because as part of our proof, we're going to want the absolute value of f of z minus L to be less than epsilon. So what we're going to be doing, and that's coming from the definition, saying that we want it to be the case that if the distance from our z to z naught here is less than whatever delta we establish, which we haven't established quite yet, we want that to correspond to that all of the points in this delta neighborhood here map to points within our epsilon neighborhood of L. And in other words, we want it to be the case that our z points in this neighborhood here satisfy that the distance from f of z to L in our second copy of the complex plane has to be less than epsilon in order to say that f of z has to lie inside of this epsilon disk over here. So absolute value of f of z minus L is the expression we're ultimately going to want to be less than epsilon. And our goal is going to be, in just a second, to say, what condition does delta need to satisfy in order to guarantee this expression comes out to something less than epsilon? That sound good?
Yeah.
So, where does that leave us? What has to be true about delta in order for absolute value of f of z minus L to be less than epsilon?
Delta has, go ahead.
Or maybe what has to be true about 5 delta, let's say?
So 5 delta has to be plus.
Yeah. Or it doesn't have to be equal to, but it has to be less than or equal to epsilon. Because if 5 delta is less than or equal to epsilon, then that, which is less than that, would also have to be strictly less than epsilon. And if we need 5 delta to be less than or equal to epsilon, Caleb, what does that tell us about delta by itself?
It has to be less than or equal to, epsilon over 5.
Oh yeah, brother. Has to be less than or equal to epsilon over 5.
So if delta's less than epsilon over 5, then we would know that all of delta is contained within epsilon, so it would still be okay.
If we knew that delta was any value less than epsilon over 5, what that would tell us is that every point within this delta neighborhood of z naught
It
here
would also be within epsilon.
has to map to something that's within our epsilon neighborhood here. So the condition that we really need in order to guarantee that points in this disk all map to points within that disk, what we just showed is that the points in this disk has to be 1/5 the radius or smaller of that disk. That as long as the radius of this disk is 1/5 of this disk or less, then every point in here, all of these points which I'm going to mark with X's, will have to map to points over here within our epsilon disk. That's what our scratch work shows, at least. Let's try writing a formal proof now to show that a little bit more formally. He'll do it okay? All right, let's write our formal proof now. Nah, I won't call Lincoln back in for this. Working. Ginger, where should we start?
Should we let epsilon be greater than 0?
I think we should. Let's let epsilon be greater than 0. In other words, we're choosing an arbitrary epsilon greater than 0 to start off our proof. The next step, just like how in the sequence proof, our next step was to pick our big N in terms of epsilon, here we need to pick a delta in terms of epsilon. So, what value of delta would you all like to pick that you think will get the job done? As some expression in terms of epsilon.
Epsilon over 5.
Yeah. If we needed that delta, that everything, our scratch work showed everything would work out if delta is less than or equal to epsilon over 5. So if delta was equal to epsilon over 5, I think that should be something that certainly satisfies that condition. So let's let delta be equal to epsilon over 5. And then what we need is if the distance from z to z naught is between 0 and delta, which is equivalent to saying the distance from z to 3 minus 2I is between 0 and delta, we want to be able to show that the distance from f of z to L is less than epsilon. Well, if we take the distance from f of z to L, what are we going to get? We're going to get the distance from 5z minus 1 plus I, that quantity, to the quantity 14 minus 11I, which, when we simplify, will give us 5z minus 1 minus I minus 14 plus 11I, which will come out to 5z minus 15 plus 10 times I. And Katrine, what should we do with that expression?
Factor out of 5.
Okay, if we factor out of 5, that'll give us 5 times the quantity z minus 3 minus 2I. Gary, what do we know about 5 times the quantity z minus 3 minus 2I?
That should be less than delta. Or no.
Less than something involving delta, but not just.
Epsilon over 5.
Well, before we get epsilons involved,
Okay.
we know this expression without the 5 is less than delta.
Oh, less than 5 delta. Sorry.
Yeah, that's gonna be less than 5 delta.
Yeah.
Mhm. Yeah, because this piece right here is less than delta, that means that the whole thing should be less than 5 delta. So far, so good? Caleb?
So are we putting in z minus z naught for f of z minus L,
So the z minus z naught is this expression right here.
right? Yeah.
And basically, what we're saying is if we take f of z minus L, that turns out to just be equal to 5 times the absolute value of z minus z naught, is what we've discovered kind of behind the scenes here. And if the distance from z to z naught is less than delta, then 5 times that distance should naturally be less than 5 delta. So Caleb, let me ask you this. What do we know about 5 delta? Or how can we relate this back to epsilon somehow?
We said 5 delta would have to be less than or equal to L epsilon.
Well, we did that in our scratch work, but from what's currently on the board,
Yeah,
what did we set delta to be equal to?
epsilon over 5.
So what should 5 delta be equal to?
Epsilon.
5 delta is going to be equal to 5 times epsilon over 5, which when we simplify, will come out to be epsilon. So Gary, that proves that the distance from f of z to L is going to be equal to something, which is equal to a thing, which is equal to a thing, which is equal to a thing, is strictly less than something, which is equal to a thing, which is equal to a epsilon. What conclusion can we draw from this string of inequalities? That the distance from f of z to L
equals the distance from z minus z naught.
I don't think they're equal. I think one is a fifth of the other.
Or
What is this? What relationship does this have to epsilon?
that is less than, yeah.
Strictly less than epsilon.
Yeah.
You got it.
Less than or equal to.
And that's what we needed to show. We showed that if we define some arbitrary epsilon greater than 0, that we could pick a delta so that if the distance from z to z naught is less than delta, then the distance from f of z to L is less than epsilon. So in other words, man, these pictures are getting crowded. We showed that if we drew any epsilon neighborhood of our L value over here, we could also find some delta neighborhood of z naught, so that all points within that are in this delta neighborhood of z naught, meaning all points that satisfy the distance from z to z naught is less than delta, are going to have to map to points that are within our epsilon neighborhood of L. Meaning all points satisfying distance from z to z naught is less than delta have to additionally satisfy that distance from f of z to L is going to be less than epsilon. And there we go, that's our proof. I guess we could wrap up by saying thus, the limit as z goes to z naught of f of z is in fact going to be equal to L. We picked an arbitrary epsilon to start. We then chose a delta from our scratch work that we claimed would get the job done. We then showed that if the distance from z to z naught is between 0 and delta, the 0 less than never really came into play here, but the less than delta totally did. We showed that if the distance from z to z naught is less than the delta we picked early on, then the distance from f of z to L will have to be strictly smaller than epsilon. Questions, comments, concerns? Let's take a 7-minute break. We'll come back at 11:15. And then we'll talk a little bit about continuity, and then I'll have an activity for you all. Hi Sarah, still hope everything's going okay. Keep up the good work getting this far into the video. Also come back in like a few 7 minutes or so. got sidetracked from my walk. Ran into Dr. Webster instead.
Oh no. You can't let that happen.
I know, I need to be better at avoiding people. Avoiding my meddlesome colleagues. Hello, Dr. Murphy.
Calculators, I'm trying to find calculators.
Dave stole them the other day, so I'm guessing it's in his classroom.
Okay, excellent.
But, Dr. Murphy needs some calculators for his 105 class. I wonder what he needs them for. Doing some geometry in there. What did the acorn say? Mathematical acorn say on the day it grew up into a mighty oak. On the day the mathematical acorn grew up into a giant oak, it said, "Gee, I'm a tree. Gee, I'm a tree." Okay, so there's one more topic I want to look at today. This one won't take us too long, which is the idea of continuity. So, Katrine, when you think of continuous functions, what do you think of intuitively?
I can draw it without picking up my pencil.
Draw it without picking up your pencil. Yeah, and oftentimes over the real numbers, that's what it comes down to. Over the complex numbers, it's harder to do because graphing functions works very differently than it does over the reals. So if you can do a complex function without picking up your pencil, and have it be legible, I would be highly impressed. But Calc 1, you kind of get a definition for continuity that we're going to be using here that actually still works pretty well, which is the idea behind a continuous function is that f of z is going to be continuous at the point z naught if the limit as z approaches z naught of f of z is equal to f of z naught. So in other words, you can take the limit as z gets really close to z naught of your function, and that's going to give you the same output as what you would just get from plugging z naught directly into the function. So like a quick example would be something like g of z equals, I don't know, z cubed plus 1 at z equals I. But the idea being, if you want to take a limit as z approaches I of z cubed plus 1, if you want to evaluate that limit, all that you really have to do is just plug in I for z into this expression, and you'll get I cubed plus 1, which is what minus I. So the whole idea behind a continuous function is whenever you're evaluating limits of that function at a point, you can just plug that point into the function to say what the limit's going to be equal to. Find the limit at z naught. You can just plug in z naught into the function directly. Which sometimes you can do, sometimes you can't. Like if I wanted to look over here at this f of z and take a limit as z gets close to 0 of this function. Gary, what would you say the limit is as z gets closer and closer to 0 of this function?
It's gonna equal 1.
Yeah, the limit is going to be equal to 1 here, corresponding to the fact that if you look at values of z that are close to but not equal to 0, you're going to get outputs that are pretty close to, well, in fact, strictly equal to 1. Caleb, what's f of 1 going to be equal to in this function?
1.
Or, not 1, sorry, I meant f of 0.
One. No.
Which condition does 0 satisfy, the top one or the bottom one?
Oh, 100.
Yeah, f of 0 is going to be equal to 100, because I explicitly defined it that way. Ginger, are these two values equal to each other?
No.
Very much not so. So what does that tell us? If the limit as z approaches 0 of the function is not the same as the value of the function at 0.
It's not continuous.
Yeah. The fact that these are unequal means that f of z is not continuous at z naught equals 0. Since the limit as z approaches 0 is not the same as the value of the function at 0 itself. Any questions or comments about that? So, one function I want to actually look at and see if we can write a formal proof of continuity for is going to be the function f of z equals the complex conjugate of z. Katrine, refresh my memory. What does it mean to take the conjugate of a complex number?
You are reflecting it over the real axis, so you're basically flipping the sign of the component with I attached to it.
In other words, we're saying that f of a plus bi is just going to be a minus bi for any a plus bi in the complex plane. I claim f of z is going to be continuous over the entire complex plane, meaning at every point in the complex plane, this function that takes an a plus bi and spits out a minus bi is going to be continuous. Here's my proof of that. Andrew, how would you expect to start a proof of this?
Let epsilon be greater than 0.
We're going to prove epsilon is greater than 0. And our goal, as part of our proof, is to show that no matter what z naught in the complex plane we choose, we're going to prove that the limit as z approaches z naught of f of z is equal to f of z naught. In the interest of time, making sure you all have a good amount of time for today's activity, I'm going to skip the scratch work for this one and just tell you what delta would need to be. Turns out, delta equals epsilon would get the job done. And here's why. And I claim that if the distance from z to z naught is less than the delta I have chosen, the distance from f of z to f of z naught is going to be, what's the distance, what's f of z here, Katrine?
Z bar.
Yeah. What's f of z naught going to be?
Z naught bar.
Yep, so this is going to give us just z bar minus z naught bar. Z naught bar doesn't mean z doesn't have a bar over it, it means you have a z naught, and then that has a bar over that. And here's where we can start using some of the properties we proved on the first day. Say z bar minus z naught bar is just going to be the same as z minus z naught with a big old bar above it. Caleb, question for you. If we have some point in the complex plane, call it z, and we take its complex conjugate, what relationship is the absolute value of z and the absolute value of z bar going to have to each other?
They're gonna be equal.
They're going to be equal. Taking the conjugate doesn't affect the absolute value. Why is that?
They're the same distance from the origin.
Yeah. If we flip over the real axis, we're not going to affect the distance from the origin at all. I would agree. So with that in mind, what does that tell us about the relationship between z minus z naught, all with a big bar over it, absolute value of that, and the absolute value of z minus z naught with no bars at all?
Should be the same thing.
Yeah, they're going to be exactly the same, just replacing z in this picture with z minus z naught. No matter what z minus z naught is, if we take the conjugate of that expression, it'll have the same absolute value as just z minus z naught by itself. Ginger, what do we know about absolute value of z minus z naught, or what are we assuming about it?
It's less than delta.
Yeah, that expression is going to be less than delta. And Gary, what do we know about delta's relationship to epsilon?
Delta is equal to epsilon squared.
So Katrine, absolute value of f of z minus f of z naught is equal to thing is equal to thing is equal to thing is less than delta is equal to epsilon. What does that tell us about absolute value of f of z minus f of z naught?
Less than epsilon.
Plus absolute value of f of z minus f of z naught is less than epsilon. And that shows that for any epsilon greater than 0, we can find a delta such that if the distance from z to z naught is less than delta, the distance from f of z to f of z naught is less than epsilon, which proves for us that the limit as z approaches z naught of f of z is in fact going to be equal to f of z naught.
Which means that it's continuous at that point.
Bingo. Which means f of z is going to be continuous at every point z naught in the complex plane. Proving this is basically the same as saying limit as z goes to z naught of f of z is equal to some L. It's just that the L in this case is going to be f of z naught specifically. So you're taking L from our function limit definition and you're just replacing that L with f of z naught. So Katrine, here's a question for you. We've shown that this function, f of z equals z bar, is continuous everywhere. Would you care to make a guess as to where this function is going to be differentiable?
Probably also everywhere.
Turns out this function is going to be differentiable nowhere.
It's not.
Spoiler alert for tomorrow's class.
It's not infinitely spiky.
Maybe it is.
We made a big deal in my real analysis class. The last 2 days of the semester, we talked about how you can construct a function over the real numbers that's continuous at every point and differentiable at no points.
Infinitely spiky.
And we had to do some power series monstrosity where we're adding all these spiky things together to make something that's infinitely spiky, so to speak. with the moral that over the real numbers, constructing an everywhere continuous, nowhere differentiable function is quite challenging. Turns out over the complex numbers, it's much, much easier to construct an everywhere continuous, nowhere differentiable function. Here's one right here. No series needed, nothing fancy, just take the complex conjugate. Everywhere continuous, nowhere differentiable. But that's a spoiler for tomorrow's class. We'll prove that tomorrow. Does anybody have any other questions about our continuity proof? Or how we showed that limit as z approaches z naught of our function is f of z naught? In that case, it's activity time. All right. How do y'all want to do groups today? I'm going to impose one restriction. I don't want group of two guys, group of two girls, mainly because I don't want group of two real analysis students, two students who haven't had real analysis. just for the sake of somewhat fairness, I'd like one student who's had a little more experience with these in each group. Ginger, give me a number, 1 or 2.
2.
Okay, 2 is Gary. So Ginger and Gary, I'll put the 2 of you in a group. Katrine and Caleb, I'm going to have the 2 of you working together today. So, activity today, relatively straightforward. I'm giving you 2 limits. One that's a limit of a function, one that's a limit of a sequence. And I want you to determine whether you think each of these limits exists, and if it does exist, prove what the limit is using the techniques we've talked about today. Sound good? Hey Sarah, I'm going to hold this one up to the camera for you so you can see. These are going to be on Canvas now as well. I don't know if I emailed this to you yesterday, but in case I didn't, go ahead and pause the video for a minute and write these down and see if you can evaluate these. Groovy. So, the first one is a function limit, so you're going to be using epsilons and deltas. The second one is going to be a sequence limit, so you're going to be using epsilon in capital N and lowercase n's.
If you're going to not usually.
I mean, we could do
Yeah, we could probably get like a number that we think it'll be, so we can get like an L value.
Yeah. For both of these, I would recommend you just start by looking at, do you think the limit does exist? What do you think the limit is? And do that before you start doing any scratch work, writing a proof, etc.
Because you could cancel out a factor of z minus 1, so you plug it into approaches 1
Oh, we can.
z
It
minus
equals 3
1
times e minus 1.
equals
0.
0. Okay, so we think it approaches 0. I think something weird is going to happen because,
Which will give us.
okay, we'll just do our proof.
Don't worry, this one's not too messy. You're just gonna need the 0 strictly less than z minus z naught for this one, because at z equals z naught, at z equals 1, bad things happen.
Yeah.
Didn't we do an example like this
3
last
times
semester
0.
when we canceled out a factor and something weird happened, so we had to make some adjustment with like rings.
Oh, I don't know what you're talking about.
Okay. So I guess we're saying, okay, this is gonna be our z naught,
Just 1. Okay.
and then this is
Equal 3
this is
times
our
1
z,
I.
and then this is our
L.
L.
Yeah.
Yeah. Okay, cool. So then scratch work.
Yeah.
Oh.
See,
Yeah, yeah.
plug it in.
Okay, so we want,
So we get rid of that
if
discontinuity.
we want z
So-
minus z naught to be 0 and delta,
What do we need? We need delta A times of
So then
epsilon.
if we plug stuff in,
So one,
we will get z minus 1 is less than delta. Okay, and now if we do,
include a zero.
oh yeah,
That's not okay.
okay, but if we do f of z, so it's 3 times z minus 1
We're just
times
doing
L, which is
arbitrary
0,
value.
we get 3 times z minus 1, which we know is less than 3 delta,
Yeah, so,
right?
and then
Why?
Z naught is 0, so.
Why did you put in f of z there? Never.
Just
Well,
less
because
than
now we're like moving
delta.
to the second part, which is like the f of z minus L.
The absolute value.
Oh, yeah,
Yeah,
okay.
and that part is now our f of z. Okay, so now if we want this to be less than or equal to epsilon, no delta, less than or equal to epsilon over
Is
3.
less than epsilon.
Okay.
And you can let epsilon be greater
I
than
agree
0.
with that, I don't know
Yep,
if you
so
wanna
now,
assume that. Isn't Z, isn't,
Oh, Z, sorry.
so shouldn't that be like Z minus C naught?
we'll go through this and then we'll figure out where we have to fix
What's your
it.
Z naught?
Because some sort of- I remember
I
something
think
we
your Z
talked
naught
about
is
before.
0, I think your L is,
But
Okay.
if we let epsilon is greater than 0, we let delta equal epsilon over 3.
so Z naught is the value that Z is equal to.
Then
Yeah, I think
if
that's what you wanna assume.
0 is less than z minus 1 less than delta,
And then you wanna show absolute value of f of z minus L, which is just absolute value of f of z minus 0, so that is less than L. Yep, that sounds good.
3
So, I'm
times
just
z
trying to
minus
recall
1
what we did here. So F of Z, absolute value of
plus
F
or
of Z
equal to 3 times z
Yeah, which is
minus
0.
1 less than
is gonna be,
just repeating that.
the
And then
absolute
plug
value
in
of,
delta here, then
what's our F of Z?
we know that that
3
part is
times
equal
z
to
minus 1
3
squared.
times epsilon. Wait,
That is not a, that doesn't look like a 3 unless you're looking in a mirror.
where's equal to epsilon?
And then
Okay.
since.
So where does it
Z
get
minus
weird?
1 is
I
greater
don't.
than 0.
Technically,
Cancel.
technically, the weird part is you need delta to also be less than or equal to 1 in order to guarantee that this expression doesn't include z equals 1 in there. Or,
Which
Oh,
equal,
because
oh,
then
here
it-
we go.
well, actually, no, I take that back. No, wait, no, it doesn't get rid of it.
Which is.
As long as
Fine,
delta's,
right?
as long as delta's greater than 0, then you know z can't equal 1. Never mind, I take that back. There is no weird point in here.
Even though that like
Epsilon
technically that isn't the original function that we're given.
Well, technically, you should have something in here like, I'm about to talk for a second.
Which means we need
Oh, we
delta.
simplified it?
That equals 3 absolute value is z minus 1 squared over z minus 1 minus 0. And then that is equal to
So-
that, but yeah.
Okay.
Proof.
Yeah. You know that that simplifies down to that because z is not equal to 1. And the reason why you know z is not equal to 1 is because you're assuming the distance from z to 1 is strictly positive.
Oh, okay.
Yeah.
So we don't have to worry about that.
I'm trying to think, what's that one example we did in class where we did have to take? I forget what it was, but I don't think you have to worry about that.
Okay.
I didn't when I was solving this problem, let me put it that way.
Okay. Alright.
Nice job.
We're done with number 1.
Oh, I really
Oh, what
contributed a lot
type
to
of
that.
Say what?
I really contributed a lot to that.
Well, when I asked the groups to explain their work, guess which one of you I'm gonna be asking to
Oh,
explain
good
what you did.
Oh.
There's a reason why I wanted to put one real analysis and one non-real analysis student in each group so that if the real analysis student does all the work, I can ask the non-real analysis student to explain.
Yeah.
But does it make sense what was going on there?
Not really.
Well, Katrina, you might want to make sure you
Okay.
understand what's going on.
Well, so basically, like, wait, so is this where you're confused?
I just, the whole thing isn't quite clicking yet. But,
Okay. Well, so the first thing we have to do is we have to find the delta.
Yep.
Okay, so if we just like, based on our definition, plug in what we have, we know that like this is the condition that we've already given you. And then we plug in 1, and then what you wanna try to do is then you move on to this like f of z minus l part, and you wanna try to make it look similar to whatever you got here, so that you can relate it back to delta. Does that make sense? So then if we plug in f of z minus 0, so it's l, we get, we can, you know, factor stuff out and simplify it down. And if we know that z minus 1, or the absolute value of z minus 1 is less than
Nice
delta, we know that 3 times the absolute value of z minus 1 is also.
Yeah, no, that looks good to me.
Because you can just say that
No.
this part is less than delta.
Does that make sense to both of you?
Yeah, it makes more sense now, trying.
Gary in particular?
Yeah,
I mean, I've been thinking about that, so that's all kind of foreign to me.
See, I think today is gonna be the day with the greatest disparity between
yeah.
having taken and having not taken
From
real
the
analysis.
center of our.
Stuff we're doing tomorrow will
to-
not stuff we discussed in real analysis really at all.
Okay.
The point has to be contained in delta.
Yeah.
Yeah. Which is good, so that means over the summer it should just take a day, right?
Yeah, exactly.
Right.
Days a week.
Time travel.
Yeah.
I don't know if it quite works out that way,
This
but
is what we think.
but yeah, looks like you two of you doing good work. I'll let you start on the next one.
Yeah, so then expression, so.
Was talking to the other group, Jinder was saying like, yeah, this took me about a week at least last semester to kind of figure out what was going on in all these groups.
confused for a long time, so don't do that.
That's exactly what I was gonna say. This is not an easy topic, and I would say easily the hardest thing we've done so far in here.
Yeah.
Also, because we did like just the, like these ones are easier, the ones with just the n and the epsilon, I feel
The
like.
sequence ones.
Yeah, I feel like those are easier.
This is why I gave you a
Oh, no,
harder,
no.
more complicated sequence than I did a more complicated than the
I
function.
need to just look at it.
Oh, yeah.
It's similar ideas, and then in both cases, you're picking an epsilon, and then you want something to eventually be less than that epsilon, some distance, but the steps are slightly different along the way. Deltas in the function.
This step is we're drawing an equivalence between the output and the input. Like delta
Yeah.
equates being less than delta,
How about your talk for a second?
and this is the output over, yeah? That's the way to
Yeah,
look at it.
it's always-
Zero.
Yeah, something that's, I think, maybe helpful to keep track is just to standardize the notation so that when you're looking at certain pieces, you always know whether it's inputs or outputs.
Yeah,
So when you see like z by itself or z naught,
yeah,
those are always gonna be input values.
So we're gonna say
Yeah.
this.
Things like f of z's or l's or f of z naughts. Anytime you see f, you're gonna be thinking of outputs. And L, when you're looking at the limit of a sequence or a function, is also always gonna be referring to an output somehow.
And this, I to the n over n.
Definitely takes some time and some practice getting used to these sorts of things, so I definitely agree.
I feel like, well, if we just move on to the next example and like getting more practice, I think that helps too.
So.
One of it has to be less.
So, limit is
So we can just flip them.
limit as n
Great.
infinity I n plus 1. Okay, so if we start plugging stuff in,
yeah.
okay, let's plug in n equal to 1. What's that gonna be?
Because
Will be
we're gonna
I.
want it to be bigger.
I don't think that'll work.
Okay.
Because I don't think
So
1 over
base of
epsilon is
1
guaranteed to be
equals
an
I plus
integer.
Okay,
Yeah,
so
yeah, yeah.
2 equals,
So we need.
You keep the 1 over epsilon, but you need a slight tweak to it.
Oh, we need to multiply.
so basically what I'm seeing is like this term is growing to infinity.
I think that'll-
Sorry,
It's if you
As
just
n
take 1
gets
over
to
epsilon and
infinity.
round it up to the nearest integer.
this term is going to 0. Cause right, you're
It's a little
gonna
bit
be
of a
dividing by
technicality,
something
but it is something
larger and
that-
larger.
Is required to satisfy the definition.
Okay.
Yeah, I think
Maybe
that's.
one, because you have a large thing over a large thing.
Okay.
Well, I is never getting
bigger. I is like always cycling between those like couple of values, but you're always dividing
Oh,
it by
you're
something
right.
like giant.
Oh, yeah,
So
so
this-
that would go to 0, so then we'll
Yeah, so I think
Oh, yeah.
okay,
Big and equal.
so now
N goes to infinity, I to the n is just gonna bounce around between a few constant numbers. So you're gonna have something small over something big will go to 0.
Go to 0, yeah.
We'll have
okay. So if we think it's approaching one,
just be one
we
over
are going
n.
to look at the distance between I to the n over n plus one minus one. And we eventually want this to be less than
Is
epsilon.
equal to 1 over.
So if we simplify this down,
Less
cancels
than
out.
1 over big N,
get I to the n over
which is
n.
less than or equal to 1 over.
So now we have to find the distance of I to the n,
That's our C1 function. Which
Which-
is.
Wait, why would you plus 1 minus 1?
because this is like our a to
Late.
the n
He's
Skipping all the algebras in your formal
Basically.
proof.
And, oh, A is what we are guessing the limit is.
Yeah. Yep, this is what we think
Oh
it
my
is.
goodness.
Okay, there we go.
Yeah.
A sub n is the original function of sequence.
Mhm.
Yep, okay.
Minus
I
1
don't
is
know
less
about this.
than epsilon.
Well, what are the possible values for I that I to the n can be equal to? There's 4 of them.
Negative one,
I negative I.
negative I.
What are the absolute value of all of those?
1. So it's 4 over
Or is
n.
it like in the space?
Yeah.
Okay, and we want that to be less than epsilon,
Yeah, it is.
so then what,
The other way you could think about this, sorry to interrupt,
No.
is I'm just getting in teacher mode, is due to the fact that absolute value breaks up nicely over products, that's also gonna tell you that if you take I, absolute value of I to the n, get a bunch of i's multiplied together, you can just take absolute value of I times absolute value of I times absolute value of I, which is gonna be absolute value of I raised to the nth power, which just comes out to 1.
Yeah.
okay,
Whoa, just crowding the other group now, huh?
This is my desk.
Not anymore, it isn't.
No.
Just
That just keeps you,
so if we want this to be less than epsilon, now we have to find
Yeah.
something,
that,
so we know that n
these both kind of make sense to the two of you?
Yeah,
is,
it's making more sense.
is it n,
Cool.
Doing it a second time.
little n greater?
I'll let you know, homework 4 is basically just like this activity sheet, it's one function, one sequence,
Yeah,
write
yeah,
proof
greater
that the limit is.
so if little n is greater than big N, then what relationship does 1 over little n have to big N?
Let's
So
see.
1 over little n has to be
Oh, I'll give you
less than
something
1
harder
over
to
n.
think about in the meantime.
Oh, great.
While they're kind of finishing up.
Okay.
So,
Which,
There's a couple pages in the packet we
so
skipped
okay,
over because
first let's
Oh,
like
yeah.
I'm
rearrange,
like,
let's
hey, this is
rearrange
just in
this
case
to
everything
n in
goes
terms
really
of n.
quickly, we have extra time.
So if we multiply both sides
Yep.
by n, we'll get 1 over epsilon, which is less than,
Yeah, we just go down here, I don't think you're gonna get too far into it, because they look
Okay.
almost done, but
Oh, is it the
z squared
Z
plus
squared?
4i.
So,
A little bit more
Now-
challenging.
over,
Yeah, so limit as z.
I think we
we do 1 over n and then 1 over e. And then 1 over n
Z
is
squared plus 4n
less than 1 over e.
equals negative 9
well,
plus
we need
4.
something in terms of big N.
Prove that.
Hi Sarah, while they're finishing up, because you're not gonna really be able to see their work while they're presenting, here's my solutions. See if your solutions match up with mine.
Okay.
I think that we can just set n,
Oh, so good, awesome, neato, burrito, yeah.
do that.
What's that called, the ceiling of 1 over epsilon?
Yeah.
So if the distance is less than.
Rounding 1 over epsilon up to the nearest integer.
Yeah.
Okay. Yep.
Yeah.
Z.
Okay.
is
So then, okay, also, for all these somehow,
minus
basically, the scratch work is the hard part, and then when you do the proof, it's just like literally redoing the scratch work, but more formally.
Formally, yeah.
Yeah, okay.
And like starting off with the let epsilon be greater than 0, let big N be blah blah blah.
f of z minus.
But Essentially, yeah.
The absolute value.
of big N equals ceiling of epsilon, okay. So then, if little n is greater than big N,
We want
Well,
this.
yeah, will be z
What's
squared
next?
plus 4.
Okay.
Yeah, because the left side is f of z and the right side is
we wanna like plug a distance in, and it's something we've kinda already
z
looked at.
squared plus 4.
For I
Oh, yeah, 4i, yeah. Wait, is it 4i? Yeah, it's 4i.
plus 9 minus 4I
What's like the first thing?
will be
In the scratch word.
squared plus 9.
The a, so that minus a absolute value.
Yeah, so we're gonna do that. I to the n minus
We can do
n plus 1 minus 1,
like a square root type of deal.
which we know is
Right,
equals,
Basically 1 over n.
To take the magnitude of this.
right, we're literally just gonna put out what we,
Less than 1 over b.
Can't quite do that because you need to know what the real and imaginary components are of the way to do that.
and
Instead,
then,
I would try
you know
factoring
that-
z squared plus 9.
And
in other words,
It turns
n
out you
is
can
gonna
factor
be
that,
greater than or equal to 1
and
over
maybe your
epsilon.
delta expression might help you determine what one of those
Over
factors
big N,
Oh, yeah. Yeah, because right in front of us.
which means if this is less than or equal to
so 1 over epsilon, which equals epsilon.
Z minus 3.
difference of squares.
which means that it is the one that exists.
Okay.
Yeah.
Proved. We didn't prove what the value. Did we prove that it is 1 or did we just prove that it's something?
We can do this,
Both, we proved that it's something and that.
You proved that it is specifically 1.
right? Because they were
By
doing
showing
this.
that this is less than or equal to epsilon.
Because here,
Because they're
using the
asking
fact that you took the original a sub n and then subtracted off 1 and showed that you can make that less than epsilon, shows that the limit converges to 1 specifically,
I squared.
where you're plugging in 1 in place of your
Okay.
a here, I guess, using that.
Because that's what we're
So we
saying
want
the this
this-
limit is.
Less than epsilon.
And so the difference, the distance between some point
Which
and
we know
1
this is less than epsilon.
has to be less than epsilon.
Once little n gets sufficiently big. Yeah, if you would replace this one here with like, if you wanted to try and show that the limit was 2, for instance, you'd have like a -2 here instead of a -1, and then the algebra wouldn't necessarily work out to be less than epsilon.
Wait, no, we defined
Because the limit isn't actually 2.
Right, it's 1, so this needs to be 1 here in order for things to cancel out nicely and actually have it work out.
Okay, what's this whole thing with the ceiling thing?
Well, you see, sometimes there's bad weather and it keeps you dry.
Yeah, okay.
Well, basically, you need n to be a positive integer, and so like, because epsilon can be anything that's greater than 0, you could plug in like, I don't know, 2.5 for epsilon in this like equation,
Yeah,
and you would get something that isn't a whole number.
okay, so the ceiling raises to the next integer up, basically.
Yeah. So if like 1 over epsilon came out to something like pi, for instance, the definition for sequence convergence requires big N to be like an integer, like a point in the sequence.
Right,
Pi is not an integer.
right, so would it break the ceiling, it would be 4 or what?
So if you did that, you would get that, and then it would just come out to 4, and then that would be a valid value for big N to work with.
Yeah,
Because if you have a little n that's greater than 4, it's going to be also greater than anything you might round up to 4, like pi as well. It's kind of the key idea here. It's sort of a technicality type thing, but analysis is a class of technicality, so.
yeah.
Oh, which we found was equal to C plus 3x squared.
What's the big N, little n distinction? Big N represent?
Like in the definition, you want big N to be greater, or sorry, little n to be greater than big N. So it's kind of like, think of this example, where like you have all these points here.
These are the ones outside, and these are all the ones out there.
Right.
After three.
I disagree with this.
Three
Right.
after.
So like,
Why?
yeah,
I don't think
like
they
in
get
the
minus
first
two
one,
minus
if
three
we have
I
big
has
n
to
equal
equal
to
absolute
two,
value of
Okay.
two plus
like,
three I.
if we have little n bigger than two,
Oh.
like, which is 3, 4,
Fill
5,
all
6.
the
Well, I want you to do correct mathematics.
Yeah.
So we want
Here's the
little n
problem.
bigger than big N,
No, I gotcha.
The complex conjugate of
which means,
z minus three I
and we're dealing with 1 over because.
is not necessarily
this
gonna
gives
be
us
the same
one
as z plus three
over
I,
this.
because z itself is not
And
a
then,
real number necessarily.
like,
If z was a real
like,
number, then
You'll
that would
always
check
get
out.
to the point, okay, so like the steps
Didn't
that
we
you
just say
take
that the
is like, first,
their
plug in what you
magnitude
have for that,
I don't think so. So like, let's say z is
like,
equal to three I
z sub
itself.
n minus z sub naught, or a sub n
What would the
minus a.
magnitude of
Like,
z minus
you
three I
just
be?
wanna like plug something in, and then simplify it down as much as you can, and you'll always get something that has like an n in it.
Cause I was
You
thinking of-
wanna set that like less than epsilon, and then you like rearrange it to
If
find
z was
out
itself
what,
a
like,
real
little n
number,
is gonna be. And then since you know,
then this would work, because then
Yeah.
you would have
Yeah.
a sort of weird interaction between the imaginary component of z and the three I. But the fact that z isn't necessarily a real number,
Okay,
sorry,
that's okay.
I give it a bonus problem to work on.
Bonus
is
power.
it a weird one?
Wow.
It's a more challenging one.
Which one is it?
It's actually in the packet. I skipped over a couple pages in the interest of time. Proving z squared plus 4 converges to negative 9 plus 4i. I think it's great. All right, let's actually talk about the 1 and 2 problems 1 and 2. Ginger and Gary, do you want to explain what you did for number 1, the function proof?
Okay, I'll.
Well, the other group's going to do 2, so
Oh, okay, alright.
I'm not going to do both of them.
Oh, that makes sense.
Gary, why don't you try
Yeah.
number 1?
Yeah, so we, for our scratch work, we find delta being greater than 0. If the distance of z minus 1, distance of z minus 1 is less than delta. And then we obviously couldn't just plugging in 1 made it undefined, like the limit, so we factored out or canceled the top and bottom, so we just were with 3 times z minus 1. And then,
Looks like you found that you needed delta to be equal to epsilon over 3 to make, to guarantee that the absolute value of f of z was less than epsilon.
so,
How did that come into play in your formal proof?
yeah, so in our proof, epsilon is greater than 0, and then delta is epsilon over 3. So then we have if the distance is less than z minus 1, is less than delta, then 3 times z minus 1 is less than 3 delta, which the 3's cancel, we're left with epsilon, and then we're left with f of z minus 0 is less than epsilon, which, 0, which is when it approaches 0.
So you found a delta so that if the distance from z to 1 is less than delta, then the distance from f of z to 0 is less than epsilon, which told you that the limit has to be 0 as z approaches 1?
Yeah.
Questions or comments? I like it. All right, Gil, do you want to try explaining number 2? Or do you feel like qualified to explain number 2, or do you rather
No,
Katrina did
I
it?
don't feel qualified, unfortunately.
All right, Katrina, why don't you explain to us then?
Okay. Basically for the scratch work,
Sorry, I can pick on you more in the future.
sorry.
so for the scratch work, we plugged in the sequence, or actually I guess even before that, we saw that as n is getting larger and larger, this term is going off to 0. So we thought that the limit converged to 1. So then we started off by plugging in like this, call it a sub n, but whatever, minus 1 into the distance formula. Then you can simplify it down and get that it equals 1 over epsilon, or sorry, 1 over n. And we know that 1 over little n has to be less than epsilon. So then through rearranging, you can get that 1 over epsilon has to be less than n. And then because you know that n has to be greater than big N, you can choose a big N equal to the ceiling function of 1 over epsilon. So, yeah, and then, let epsilon be greater than 0, let n equal the ceiling of 1 over epsilon, and then just repeating this algebra that we did here. When you get to this 1 over n part, because you know that little n is greater than big N, you know that 1 over little n is less than 1 over big N, and then you can plug in 1 over epsilon for big N, since you know that big N has to be greater than or equal to 1 over epsilon. So yeah, once you plug that in, you get it equals epsilon, and then you know that this limit converges to 1.
Questions or comments? Nice job. All right, I think that'll do it for today. So homework 4, which is up, is basically just like this activity sheet. I'm giving you one function limit and one sequence limit, and your job is to prove both of them. So I encourage you to take a look at that before tomorrow's class. When we come back tomorrow's my favorite day of week 1, one I've been excited about. Probably my second favorite day of the semester. We are going to be talking about differentiability of complex functions and derive our first Cauchy result of the semester. The Cauchy-Riemann equations, partial derivative stuff we mentioned in passing yesterday. Hope you all have a good one, and I will see you all for week 5 of the semester.
Bye.
It is, yeah. Be a third of the way done, actually.
Actually kind of nice how everything condensed.